Welcome to Fun with Science, Engineering, and Technology. At Melissa's request today, we're going to do a very brief demonstration of some light things, and if everything goes wrong, Catherine, we can blame her. It's her fault because she picked the subject, and so what we're going to do. So lights, we have lots of light, right? All the lights in here in the studio. What is light anyway? You have any idea?
A wave?
It's a wave?
Yeah.
You mean like this? Well, we can all go like this, huh?
No, a wave of something.
Energy.
It's
Yeah.
energy. All right. One of the theories about light is it's an electromagnetic wave, right? When we talked a little bit about waves, we talked about sound waves, right?
Yeah.
The compression of the air and expansion of the air as we're talking, right? And it can go over, the sound waves can go over and hit the wall. They can bounce back, right? The same thing, light waves, except light waves don't require the air, right? Because we can get light from the sun, and it's traveling through space, which is a vacuum, right? So but it is a wave, all right? But it's a little different than the sound waves. It's an electromagnetic wave is one theory of it. So electromagnetic waves are the same kinds of waves that are carrying the television signal out to the television sets. When you turn your radio on in the morning, you get the radio signals coming in. All right, those are radio waves coming. Right, so there's all kinds of, and they're electromagnetic waves, a little different than sound waves. And light falls in that same category. X-rays are electromagnetic waves. Right, so, and the difference between all those different waves is the frequency, how fast they vibrate. Right, radio waves are down a pretty low frequency. If we take a look at our little chart that we have here, right, the lowest electromagnetic waves that we have are down in the radio wave range, right? And they're very low frequencies, comparatively speaking, right? We go up in frequency a little bit. This chart starts low frequencies here and goes to high frequencies on that side. And as we go across, right, after the radio waves, then we get microwaves, right? What do you think of when you think of a microwave? Cooking your hot dog, right? Because you have the microwave there, and you go up and you throw your food in it, you punch the button, and it cooks it. How does it do that? It does it with electromagnetic waves, right? In fact, the microwave, right, actually has a vacuum tube on the inside of it, right, which they use in radars. You know, the radars like the Doppler radar you see on the radio, and the radars that track all the airplanes back and forth. Well, most of those waves, electromagnetic waves, are generated for the radar, all right, are generated by a tube called a magnetron, right? And your microwave actually has inside of it, up on the top of it usually, is a little magnetron. So when you turn it on, it's up there and it's generating all these electromagnetic waves, which radiate down into the cavity of the inside of that microwave. And if you got something in there, right, those radio waves are going to make the molecules in it start vibrating back and forth like this and heat it up. Right, so that's what, if you throw your steak in there, punch 3 minutes or whatever it is, right, and it generates electromagnetic waves, right, which are going to actually make the steak heat up and cook. And if you were out working around the radar, right, and you got up in front of the antenna real close, right, the microwaves coming off of that radar antenna, right, could cook your hand, it could burn it. Right, so you have to be very careful when you're working around some of those radars, which are very high frequency, very high powered. Right, so we have, then that's microwaves right there. Then we go up a little bit higher in frequency, where it's vibrating back and forth a little bit faster, and we get into the infrared range. What's infrared?
I don't know.
You're experiencing it right now. And you don't know what it is. Huh. Those lights up there, how do they feel?
Hot.
Hot, right. Right. And the reason that it is because they're generating some heat, which is infrared, electromagnetic waves that are coming off the light down here and hitting you and causing you to warm up. Sort of like the microwaves, right? But it's not as dangerous as the microwaves. It's not cooking you, but it does make you feel warm, right? And that's like the heat energy, so infrared, right? And then we go up a little bit further, right in there. Let's see that little tick there?
Yeah.
That's visible light. That's what we can see. It's a little bit higher. It's up above the infrared, right? Above this, a little bit higher than the heat waves in frequency, right? So we've got light right there. So a little bit. That's what we're going to talk about. Is that little itty bitty piece right there? But let's look at the rest of it. Go a little bit above it, and what do we get?
Ultraviolet.
Ultraviolet. So on either side of that little bit, right, we have infrared on the low side, and to go higher in frequency, we get to ultraviolet. Remember that. That's a key to remembering this light stuff. Right, then we go a little bit higher, right, and we get some what is called soft X-rays, which are again electromagnetic waves. Right, and they can. What about X-rays? What do you know about X-rays? You said you were going to volunteer at the hospital. You should know something about X-rays.
You can take a look at your bones and see.
You take a look, and what it is high-frequency electromagnetic waves, and what they do is they put a piece of photographic paper behind you, basically, and then they shoot all these electromagnetic waves at you, and they can pass through the soft tissue, right? But they get sort of blocked by the bones, by the denser material, right? So the less dense material, they go right through and expose the film behind you, where there's a bone, right? They're blocked, right? And they can't go through, so you see like a shadow on the X-ray film. Where else do you get X-rays from? Those people out there that are watching us right now are getting a little dose of X-rays, right, off of their television set. Because the way they generate X-rays is they got a real high voltage, and some electrons are banging against a plate, right? And when they do that, when they hit the plate, they generate those X-rays. The same thing happens in a picture tube, unless they got one of the new fancy plasma tubes, right? But if you got one of those old-fashioned picture tubes, the electron, it has a gun in there, like called an electron gun, which is shooting electrons up to the face of the tube. And when it hits the face of that tube, if they're going fast enough, they generate a few X-rays. So you're sitting in front of one of those old-fashioned TV sets, right? You're getting a little dose of X-ray. Not enough to normally hurt you, right? But you are getting some. Then you go a little higher in frequency, we get some hard X-rays, right? And then we go even higher than that, and then we get some radioactive waves called gamma rays, right? Which you would get if you had an atomic explosion. So right here, visible light, the stuff that we can see with our eyes, right? Just below it is what?
Infrared.
Infrared, and just above it is
Ultraviolet.
ultraviolet. Okay, so now, if I take a look at the lights coming down here, what color are they?
Yellow.
They're yellow?
Yeah.
Are you sure they're yellow?
A clear.
I had this problem with you girls on the bicycle, right? They look white to me. Right? If you look at your shirt, my lab coat, what color are they?
Right.
They're white. If we had yellow lights or something, then it would my shirt would be yellow, right? Your shirt would be yellow. So that's white. Those lights are white. They're not yellow. So what does that mean? You have an idea? No?
No.
Why are they white? Why is her sweater sort of blue? Why do we have all those colors back there on the background? We got some blues, we got some reds, we got some oranges, greens, yellows.
I don't know.
You don't know?
No.
What if I were to take you? We're going to go down to New Mexico now. They have a big cave down there called Carlsbad Caverns. And one of the things that they do to all the tourists to go through is they take you down the cave. You're down about 25 stories underneath the ground. They turn the lights on. What do you think happens?
It's dark.
It gets dark. right? But it's not the same kind of dark we have in here. If you go in here, if we were in here at night and we turned all the lights out, after a while, what would happen? You'd be able to see a little bit, right?
Your eyes adjust.
Your eyes would adjust and you're able to see. And the reason that you're able to see because there's still a little bit of light. There's some starlight, there's some moonlight, there's some lights outside that are, you know, coming through the windows. So you're able to see a little bit. But when you get down into the bottom of the cave like that, and they turn the lights out, there's no light.
Can't see.
You can't see anything, right? You hold your hand up like this, you can't see your hand because there's absolutely no light. And the only reason we can see this is why can't I see my hand now?
Because of the light.
But why? My hand's not generating any light, is it?
No.
So what's happening? Is that light up there is coming down, hitting my hand, bouncing off, back to my eyes, and my eyes, the little electrical signals going back to my brain, right, which is working very, 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 very fast. And it says, ah, he's got his hand held up. Okay? But if I take and I look at this piece of paper, this is the same color as my hand. The reason I can see this piece of paper is why? If I were to take this down to Carlsbad Caverns and turn the lights out, would I be able to see it?
No.
What color would it be?
Black.
It would be, yeah, it wouldn't be anything. I couldn't see it, right? But so now that I'm taking a look at my hand, I look at the paper, are they the same colors?
No.
No. Why? I can see both of them. I can see both of them because they're doing what? They're reflecting light back into my eyes, right?
Yeah.
But they're not the same color. Why is that? Okay, let's see if we can figure out why.
Okay.
Okay, so what I'm going to do next, what color is that light?
White.
Right.
That's white? It's white light? Okay. So, I'm going to come over here. We're going to take, this thing's called a prism. It's a little triangular shaped piece of plastic, all right? So what we're going to do is we're going to do this. If I can get it just right. This is the part.
There
where
was a rainbow.
There was a rainbow
Yeah. Right there.
right there. Okay. Now then, so what's happening is I'm shining my white light through there, right? And what comes out the other side?
Different colors.
Some colors, right? I got some blues, and I got some, if I look at it real careful, I got some yellows, and then I got some reds, and I got all those different color of light. So what that piece of plastic's doing what?
Reflecting light.
It's,
Colors.
is it changing my white light color?
No.
Yep.
It's still white.
This is still white, right? But why does it come out over there and I have all those different colors on the other side?
I don't know.
You don't know. All right. What do you think would happen if I took? Let's take a nice. I'll make my light red. Right. I put a piece of red filter paper over it. All right. So that I got red. Right. Now then, if I take my prism and I put it in there, what comes out on the other side?
Red.
Why is that? Because
The light.
the reason it is because this white light has all the colors in it, right? It's made up of all the colors. And somehow, right, the prism, when I put the white light on it, right, what I'm doing is I'm breaking up those colors. I'm taking that white light and I'm breaking it up into a little spectrum, right, so that I got some blues and I got some greens and I got some yellows and I got some reds, right? But when I took and put
The red on
this little filter across the top of it, the only light that I get out of there is
Red.
red, right? Because it's blocking all the others. If I were to take and I were to put a green one on there, What's happening?
It's green.
It's green. So, but look at your shirt now. Why is that spot there green?
Because the light is green.
Well, why is the rest of it white?
Because the other light's shining on it.
Because the other light's shining on it. Right, but only the green light's being reflected off of there. So what if I took
Oh.
a red, I have a red one, and I have a green one, and I'm going to put both of them there. Well, what happens?
I don't know. Oh.
What happened to the light? It sort of faded away, right?
Yeah.
What? Hold those for me. Give me a blue one. All right, we're going to take a red one, a green one, and a blue one. You're going to put those together. Now then, what happened to it?
It went away.
Went away. Look
Even
here. We can hardly see it. If we taken, it sort of went away. Why?
Because the light
Yeah,
can't go through the colors. All
The light went through this one, which makes it green,
But if you put all the colors together,
right? And it went through this one because it's red.
when you put them all together, it's too thick. The color.
What put them all together is too thick,
Well,
and this one is blue. Why does this look blue instead of white?
because the
This one's-
filter's blue.
This one, okay, it's because the filter is blue. That's
Yeah,
right.
and
Okay,
the
but
light-
why? Why does that blue filter make it look blue?
Because when the light goes through the filter, it reflects the blue color.
No, it lets the blue color pass through, and it stops all the others. So when I put that blue filter on it, right, the only part I can see is the blue light. The white light is all colors. It's all those colors added together, right? Makes the white light. But if I take this blue filter and I put over it, right, I only allow the blue light to get through. It blocks the greens, it blocks the yellows, and it
red.
blocks the reds, and all those, right? So the only one that I get through there then is the blue, right?
Yep.
So now then, if I take a blue and a green and I add them together, I'm blocking everything except the blue and the green, right? So it gets less, right? If I take all three colors and I put them on there, right, and what happens? It blocks out almost all the light. And my filters aren't very good because I made these on my printer, all right? But if I had some real good filters and I took those three colors and I put them over here, it would block out all the light. I wouldn't be able to see it because they would block out. This one only allows blue to pass. This one only allows green to pass. This one only allows red to pass. So when I put them all three together over top of my lens, I get nothing. No. So, light, right, if we look at that little spot that we have there, right, that little visible light, right, down below it is, what did we say it was? Infrared,
Oh, yeah.
right, and above it is
Ultraviolet.
ultraviolet. So that's sort of a little clue to something, right? And what it is this little spectrum. If we took that little spot there, right there, and we blew it up, right, the colors would look like this. The red would be down at the lower frequencies, infrared, right, down here. And then we go up to
Violet.
violet on the end, which is blue. So if we look at it now, right, we've got down here is the red, then it sort of goes to orange, then it goes to yellow, and it goes to green, and then it goes to blue, and then there's another little color in here, indigo, and then violet, right? And if the reason, way to remember that is this guy, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Sometimes you'll see them leave out the I for indigo, because not too many people know what indigo is anymore. But it's a color. It's sort of in between blue and violet. Okay? And this would be, the red would be low frequencies. The violet would be a higher frequency. The green would be Medium, it'd be a in-between frequency, right? Yellow would be down in here, right? So as we go across the chart like this, the frequencies increase. Now, I knew I was going to do that. If you look at that, tell me about the pencil.
It's orange.
Okay, what else? Look at it on this side. Is it straight?
No.
No. It looks like when it comes down and goes through the water,
Curve.
it's bent a little bit, right?
Yeah.
So, wonder why that is. It's because of something called refraction. You know, you heard of reflection, right?
Yeah.
You get up in the morning, you look at the mirror, and what you get is a reflection, right? Because the light is bouncing off of you, hitting the mirror and bouncing back so that you can see it, right? And that's a reflection. This is refraction.
Refraction.
Right, refraction. And what refraction is reflection is bouncing the light back to you. Refraction is bending the light a little bit, right? And how much it's bent is dependent upon the frequency of the light and a characteristic of the material. In our case, the material is water, called a refraction index. Okay, different materials. If we were to put molasses in here, right, and stick the pencil in there, then it would look like it was bent a little bit differently, right? A little bit more, a little bit less, depending on what the index of refraction is for molasses, right? So, all materials have some sort of index of refraction, including my little prism, right? So, as light beam passes through the prism, it's going to bend a little bit. And depending on what this is, a piece of plastic, but we could have a piece of glass or whatever, different kinds of glass, and the index of refraction, how much it's bent, will change depending upon the material that we have. The other thing that determines how much it's bent is the frequency of the light passing through it. We said red was what?
Low.
Low frequency, right? So when the red light comes through here, we take this white light we have out of my flashlight, right? We shine it through the prism. Right, the red part of that, the low frequency part, is going to be bent a little bit. Right? The blue part, or the violet part, which is higher in frequency, is going to be bent more. Right, so red gets bent just a little bit. Blue gets bent a lot more. So we take my prism, go back here again, and what's happening? Look, where's the red?
On the outside.
It's on the outside, right? It's closer to you, right?
Yeah.
So there's the red light from my flashlight goes through here, and it hits the prism, right? And it's not bent as much as the blue. Where's the blue or violet?
Closer to you.
Closer to me, so it's bent more. So what's happening is the blue light comes through and it's bent down this way, right? The red light comes through and it's not bent as far, and it's over that way. How about that? And to see a picture of it, we look back over here, right? Here's our prism, and this is what's happening. Right? Here's the white light coming in, represented by this black line, right? Because it wouldn't have worked too well if we'd have put a white line on there. We wouldn't have been able to see it. Right? So it comes in, and it goes into the little prism here, right? And this white light is made up of all the different colors, right? Roy G. Biv colors, right? The red, being a lower frequency, comes through, and it's not refracted as much, right? So it's not bent down as much, so it appears over here, closer to you. Just like when we were using my prism there. The blue, or the violet light, is coming out of my flashlight. There is violet light coming out of there. We just proved that. Okay? It's bent more because it's a higher frequency, so it appears down here. just like when we held the prism up there. Is that important to us? Is it really important? Do we really care? Hmm? Do you really care that that happens? Sure you do, right? Because it's a very important part of our life, right? Everybody enjoys a rainbow, right?
Yeah.
You've chased all those rainbows and trying to find a pot of gold at the end of it. Well, the rainbow, the little water, the reason we have rainbows, little water droplets, right, do the same thing. They act like little prisms, right? And the sun's shining through them, and you get some reflection off of a cloud somewhere, and that's what you see as a rainbow, or a reflection off of some of the raindrops, right? It takes that white light from the sun. I know the sun sometimes looks yellow because its filter comes through the atmosphere, but it's really generating all the light frequencies, plus some other electromagnetic frequencies are coming off the sun too, like ultraviolet, right? That's why when you don't want to go out in the summertime and hang out in the sun too long, because the ultraviolet is going to cause you possibly to later on have skin cancer because it causes some damage to your skin. But we have rainbows, right? The other thing, which is a lot closer to us right now than what you might imagine, is that same thing happens, or could happen, in the lens of the television camera, right? And if we don't do something about it, because that lens is a curved lens, right? And what it's going to do is, as all the different colors of light come through the lens, right, they're going to be bent a little bit, right? So they get bent, and what people at home are going to see, be seeing you, and around you there would be this little rainbow kind of an affair, right? And you would look sort of funny, of course, right? We don't get that because they do some spatial coatings on the lenses and do away with that little effect. But I have a very, very cheap lens here, and if we're real careful, we may be able to see it. Okay, I'm going to put it over my flashlight, right, like this, and I'm going to turn it on, and if we adjust it just right, we're going to be able to see right there in the middle. Look at we got on the outside. We got a little yellow, and in the middle it's indigo. What's a little white wormy looking thing? See that?
Yeah.
Point at, take the pencil and show everybody where it is. Right there. You know what that is?
What?
You don't know what that is?
No.
Strange, isn't it?
Yeah.
Where did it come from?
I don't know. What is it?
It's the filament in the light bulb in my flashlight. Okay, what we've done was we've magnified it a little bit, and what we're looking at is right there is the filament in that little curly Q thing. If we were to turn this off and we go down in here with a magnifying glass and look at it, we could see the filament in that light bulb, right? This little spiral wire, right? That's what that is. So, why is your sweater blue?
Because when the light goes and you can only see the color blue.
Because when the light's coming down and striking it,
It blocks out all the colors except
it's
for blue.
only reflecting the blue. It absorbs all the other colors, right? Your shirt is white because
You can only see the white.
because I can only see the white. Why? Because the light comes down and strikes it, and it's reflecting
Only white.
only white. Only white is
All
what?
the color.
All the colors, right? My shirt is green because all those colors are coming down, hitting it. They're all being absorbed except the green part, and the green part is being reflected. So when we look at it, we say, oh, what a pretty green shirt. Right? We look back there, and the background, right, is blue. And why is it blue?
Because
When the light
touches
comes.
it, you can only see the color blue.
Because when the light touches it,
No, when the light reflects that
Off of it.
blocks out all the
Yeah.
colors except for blue.
because it's going to absorb all the colors except
Blue.
blue. right? The pink part up there, right? It's absorbing all the colors except pink, right? The green,
Except for green.
it's absorbing all the colors except the green colors. We're hitting that background with all the colors, right? And what we're seeing are the ones reflected, right, from the different parts of the background. Where it's pink, it's that portion right there is back here. This point right here, right, is absorbing all the colors except pink, right? What's this one doing? The W.
It's reflecting on the color.
It's reflecting all the colors. It's not absorbing any of them, right? If it, of course, that's sort of a generalization because the white is not really pure white, so but it's pretty close. How about the little orange thing up in the corner there?
It's absorbing all the colors except for
orange.
orange.
All the colors except the orange, and it's reflecting the orange back so that we can see it. The green tree,
Absorbing all the colors except for green.
this is absorbing all the colors except for the green, and it's reflecting the green backs. So what we're seeing are the colors that are reflected back. Okay? And whenever we take our prism and we get it all set up here right, where we can see it, right? I can see some violet. What's that mean?
High frequency.
That's a higher frequency, right? It's the highest frequency we can get in the visible light. And the reason we can see it is because it's being reflected off of that white piece of paper, right? And the orange,
Low frequency.
it's a lower frequency. And again, the reason we can see it is because the only color that's striking the white piece of paper right there is orange, and it's reflecting back and we can see it. So, if the frequencies right below visible light are called what?
Oh, infrared.
Infrared.
Infrared, and right above is
Ultraviolet.
ultraviolet, and the ultraviolet causes us what kind of a problem in the summertime? Causes you sunburn, right? And if you get enough sunburn, eventually possibly you risk skin cancer. The infrared, do we have any infrared in here right now?
Yeah.
Yeah, from the lights, right? And that's the heat. And if you watch the TV now, all the soldiers right over there with those funny cameras where everything is green. They're if you watch some of the newscasts, right, and you see all these green pictures that they had on television. The reason they're green is because of the display that they're using, right? It comes out green. But what they're looking at is the heat off of all those, the infrared off of all those things out in front of them, whether it's a tank, a building, a person, or whatever, right? So at night, right, when there's not enough light to be able to see, they use those infrared detectors, right, which watches the heat, right, being radiated from various and sundry things, people, plants, buildings, what have you. So that's how they get those pictures. Right, so why is this all important to us? Because we like rainbows.
Yeah.
That's right. we like those rainbows. That's really why it's important, okay? And we need to know about the ultraviolet and the microwaves, right? Microwaves, what do we use them for?
Cook food.
Cook food. Where else can you get your microwaves from?
What?
Where else do
Radio.
microwaves come from? No. Radio is a little lower frequency. Radio is the lowest end of our electromagnetic spectrum. But where else? Those folks out there watching TV on one of those old TV sets,
Oh,
they're doing what?
it's the tube of color.
Okay, they're getting some X-rays back, right?
Yeah.
They're getting X-rays. So where else do we get microwaves? Radar. The radar that you see on the television in the evening, or the Doppler radars that they have. Okay, those are all microwaves, and just like the frequencies that you have, which you use to cook food with. Right. So I think that's for today going to be it. And be sure the next time you see a rainbow, remember this is important. Right? And white is all what?
All colors.
White is all colors. Black is
No colors.
no colors, right? If we were to go down in Carlsbad Cavern as they turn the lights out, and we look at my hand, We're not going to see anything because there's no light being reflected off of it. All right, thank you very much. And remember, the next time it's raining and the sun's shining, run out and look for a rainbow. You'll enjoy it.
Stay there.